Well, I'd like to do an example of the Bode plot for you today. Give you a look at how we can apply the theory that we've been talking about. I'm going to create the magnitude and phase plot, a log-log Bode plot, for a transfer function that I'm just selecting because it's got a little bit of everything in it. So we will have some gain. We'll have a pair of complex conjugate zeros. We'll put a pole at the origin, and we'll put a pair of complex conjugate poles. So here we have 250 times s squared plus 100 divided by s times the quantity s squared plus 10s plus 2500. I'd encourage you to take a look at these complex conjugate zeros and poles with a quadratic formula. What you should find is that you've got a pair of complex conjugate poles here, clearly right on the j-omega axes, and these are off the j-omega axes. They're stable by a little bit. Zeta is 0.1. The first step is we're going to take this apart and look at the various components that we're dealing with. In gain kind of terms, we have a 250 in the numerator, and we've got the 100 from the pair of zeros in the numerator. We don't have a gain term associated with the pole at the origin, but we do have gain associated with the complex conjugate pair of poles. Next up, we have a pole at the origin. We have a pair of complex conjugate zeros. As we mentioned, s divided by 100, s squared plus 1. And then we've got our poles. S squared divided by 2500 plus 10 over 2500 s plus 1. Just barely enough room on the piece of paper here. What you should see, taking a look at this whole thing, is that we have a gain of 10. We have a critical frequency at the origin. It happens to be a pole. Up here, we have a pair of complex conjugate zeros. Critical frequency is 10 radians per second, the square root of this number. If you went and looked at it through your quadratic equation, you'd see that this is 10 radians per second from the origin. Complex conjugate zeros, and then lastly, complex conjugate poles at omega n, the critical frequency of 50 radians per second. So gain, critical frequency at the origin, critical frequency at 10 radians per second, and a critical frequency at 50 radians per second. So I'm going to use a piece of Bode paper. So I've just created a piece of paper here with some scales on it, and I'm going to go ahead and looking at critical frequencies between kind of the origin, 10 and 50 radians per second. Why don't we go ahead and put 10 right there? Makes this 100, makes this 1000, 1 radian per second, 0.1 radians per second, 0.01 radians per second. We're scaling this omega axis. The first thing we got going on is a pole at the origin. So we're going to be seeing a line at 45 degrees cutting through, associated with that pole at the origin. It has a gain of 10. And so if we wanted to put some scale to the gain here, at 1 radian per second would be a great place to throw our gain of 10. We could call this line linear 10, or I'm going to go ahead and call it 20 decibels. So here we got the magnitude of G in decibels. And I'm going to go ahead, it's a decade scale going this way, so this must be 0 dB minus 20 dB minus 40 dB. That's the Bode plot we would get if we only had the gain and the pole at the origin. But we don't, we have more. And so we're going to find that there's a pair of complex conjugate zeros. They're at 10 radians per second. It's the next thing that we hit. They're right on the j omega axis. So at this frequency, 10 radians per second, we're really going to go through 0. And it's going to be quite sharp. We're really going to go through 0. But the zeros, 2 of them, are going to bring the slope from minus 20 dB per decade from our single pole to 0 dB and up to plus 20 dB per decade. We're going to see the line break with a positive 45-degree angle, positive 20 decibels per decade. Again, that's stepping up from what we were doing by 40 decibels per decade. So 1 0 would take you from here to here, the second 0 took you there. And that's what we would get if all we had was the critical frequency at the origin and the complex conjugate poles. The complex conjugate zeros. But at 50 radians per second, we have a pair of complex conjugate poles. Now, I put these little minor marks between my decades here. In rough terms, 1, 2, 5, 10, 20, 50, that's a logarithmic scale. So if this is 10 radians per second, 20, there's 50. Right here, we're going to start to break in the direction going down 20 dB per decade. So try to make a nice 45-degree angle there. And that's what we've got. We've got a system that has a magnitude response that comes in like this, goes all the way through 0, starts coming back up with a zeta of 0.1. You might see a little bit of peaking here. It comes back down again. That would be the magnitude response that I'd expect from this transfer function. Now, as far as phase response goes, might as well put 0 degrees here, plus 90, minus 90 degrees. I chose these because I don't see anywhere on this plot where there's more than 90 degrees of phase shift, because we'll get 90 degrees from each pole and 0. And so we're going to start at minus 90 due to the pole at the origin. When we come through the complex conjugate zeros, we're going to pick up 180 degrees. They're right on the origin. Zeta is equal to 0. It's going to be an almost instantaneous phase transition. And then again at 50 radians per second, because this axis is right on top of the other one, we're going to lose the 180 that we just gained. There's a little bit more of a transition there. We'll go exactly through 0. But with a zeta of 0.1, we'll see a fairly fast transition, but not instantaneous like we did with the zeros. So here you have it. This is the perhaps best estimate hand sketch for the angle of G. We've got the magnitude of G sketched. This would be a reasonable representation, hand sketch, for a transfer function, magnitude and phase response for a transfer function that we started with here. Thanks. Good luck with this stuff.